among the following statement, all are regarding adsorption. So we have to find which of these option, that is 1, 2, 3, 4. In each option there are actually two statements. In option 1 it is BC, then AB, then DA or CD. So which one of them will be correct, that you have to find out. The first statement is saying that del H becomes less negative as adsorption proceeds. Okay, so what happens when there is increase in absorption, the sites available, that will be gradually decreasing. So as it is exothermic process and it proceeds, number of active sites present over the adsorbent decreases. So that is the reason now the process gradually it will be less and less. That is, as time will increase, gradually the process rate will decrease and ultimately less heat will be revert. So when the process will just start, then there will be huge amount of energy liberation, but as it is going on, gradually the process will be slow. That means here less negative will be the value. Less negative means now energy evolution, that amount will be less. So that is why it is less negative. The numerical value, if we consider, that value will be very small, and as there is a negative sign before that, that means it is less negative. So this statement is basically correct. Okay, now as it is correct, obviously we can cancel out these two, because in these two we do not have any statement A. The next statement, on a given absorbent, ammonia is absorbed more compared to nitrogen gas. Now ammonia and nitrogen, if we see, first of all, it is already discussed that critical temperature, it has relation with the liquefiability of the gas. So if CT, that is critical temperature, is very high, that means it can be easily liquefiable, and this type of gases, their tendency to absorb, that is obviously high. Now as CT is high for NH3 compared to nitrogen, so that is the reason ammonia will be absorbed more than nitrogen gas. So this is one way you can describe it. Another way also you can describe it, and the second method is NH3. If we look at this molecule, it is obviously more polar compared to nitrogen, because nitrogen, it is symmetrical structure. Okay, so as it is more polar, so that is why its interaction with the absorbent surface, it will be more, so that is why it will be absorbed more. So you can explain it from polarity or the critical temperature value. So NH3 has high force of interaction on absorbent due to its polar nature, and the second way that you can explain is that its critical temperature is higher compared to nitrogen. So B is also correct. Now as B is correct, obviously it will be option 2, right? Now come to the third statement, we will see why it is not correct. On absorption, the residual force acting along the surface of the adsorbent, that is increasing. So residual force acting along the surface of the absorbent after absorption, whether it will increase or decrease. Now as the absorption increases, that is after absorption, when the process is going on, the residual forces over the surface, obviously it will decrease. It cannot be increasing. That is not true. Okay, because when there is no absorption, that is the process is not started yet, then residual force will be maximum. But as soon as it is started, gradually residual forces, it will be decreasing. So this statement is not correct. And the last one, with increase in temperature, equilibrium concentration of adsorbate increases. Now with increase in temperature, this process is increasing, that means the process must be endothermic. But if we consider physical absorption, the process is exothermic, and that is the reason that with increase in temperature we cannot say that equilibrium concentration of adsorbate increases. And also in case of chemisorption, with increase in temperature, first it is increasing, but once the activation energy is that is the requirement is fulfilled, after that with increase in temperature the process will not that is the rate of the process will not increase. So this is for chemical absorption. But here if we look at the statement, in general we cannot say that this is true, This is partially true for chemisorption, but we have to also consider physical absorption. Okay, so the process is, that is physical absorption. Actually absorption itself is exothermic, but still in case of chemisorption compared to physical absorption, more temperature is required because here activation energy is involved, which is not involved in case of physical absorption. But in general, that is as a whole, adsorption is exothermic, so that is the reason on increasing temperature obviously the equilibrium will be shifted towards backward direction. So concentration of adsorbed particles cannot increase, it will be decreasing. So the, actually I should not write it here, it will be here T, T, F and F, because the correct statements are written here. Okay, so here which option will be correct? It is A and B, because other two statements C and D are not correct. Okay, option 2. With respect to drug enzyme interaction, we have to find out wrong statement. So there are 4 statements that are related to drug enzyme interaction, and we have to find out which one is wrong. But before discussing this question, I would like to mention here what is enzyme inhibition and what are the different types of enzyme inhibition. Okay, so enzyme inhibition, we can also call it reversible enzyme inhibition. So there are actually 3 types: competitive, non-competitive and uncompetitive. Okay, and among these 3, the first 2 most common. So when it is competitive, basically the inhibitor that will be interacting in the active site. Now we know that active site is that site of enzyme where the substrate is attached. Okay, but if inhibitor is already taking that place, so substrate cannot approach. So that is why there is a competition between inhibitor and the substrate. Now if it is drug enzyme interaction, the substrate is drug, so that is why it is called competitive inhibitor. So this is common, but see, there is another site present which is not active site, but this has a special name which is known as allosteric site. So this site is not active site, but this is another site which is known as allosteric site. So sometimes what happens, the inhibitor, it is not approaching towards the active site, but what it is doing, it is now interacting in the allosteric site. So as a result, what happens, the shape of this active site is now changed. See, previously the shape is like this, but now it is round shape, but substrate, as it has complementary structure like the active site, but now the active site shape is changed because non-competitive inhibitor is interacting in this region, so that is why the shape is changed. So as a result, substrate cannot bind. So here also we are getting inhibition, but it is not direct inhibition, as if it is indirect inhibition. Why it is indirect? Because here inhibitor is not approaching towards the site, that is active site, where substrate is basically present. So that is why there is no competition. So the name is non-competitive inhibition. Inhibition is there, but there is no competition between inhibitor and substrate. So that is why the name is non-competitive. And the third possibility, which is rare, but still we should know it, uncompetitive. So uncompetitive means that the inhibitor, it interacts with the ES complex, that means enzyme substrate complex. So first substrate is bind with the active site, and then the inhibitor is approaching towards this complex. Okay, so this is the third possibility. Now allosteric site, here we have the definition: the place on an enzyme where a molecule that is not a substrate, that is inhibitor, it may bind, and thus what it does, it changes the shape of the enzyme, and as a result there is direct influence whether substrate now it will be able to bind to the active site or not. Okay, so it is influencing its ability to be active. So now the activity of the enzyme, it is no longer present because this inhibitor, it is attached to this allosteric site, and as a result the shape is changed. So now substrate cannot recognize the shape because now the shape is not complementary, right? So this is allosteric site. So basically when we will say non-competitive inhibitor, then it is actually allosteric inhibitor. So any of the name we can use, and if it is competitive inhibitor, that is the first case, that is the most common case. So now we will go back to the previous question. Here in all these terms we can see non-competitive inhibitor is mentioned, then allosteric inhibitor. So these three are basically same, because non-competitive inhibitor is all another name of allosteric inhibitor, okay, and competitive inhibitor, that is the first type. So here also we have another picture which is allosteric inhibition and allosteric activation. So what is the difference between the two? See, this is the active site which is half circle type, and this is allosteric site. Now the inhibitor is approaching here because there is a proper matching, and after it is attached to this site, now the shape is changed. So now it is altered active site, so substrate cannot approach. So that is why it is known as allosteric inhibition. But sometimes the opposite may be the case. So now we are not using the term inhibitor, now we are using the term activator, because it will help the substrate to recognize the enzyme, because initially the shape is like this, but when the activator is approaching in the allosteric site, then the shape is changed to that shape which is complementary to the substrate. So now it is actually helping the substrate to recognize the enzyme. So obviously it is activation, okay. Though here the question is related to inhibition only, not activation. So see, among these four, one of them will be false. Non-competitive inhibitor binds to the allosteric site. It is obviously true. They cannot, they do not approach to the active site. Competitive inhibitor approach active site. So this is also true. This is correct. This is also correct. 2 true. This is also true. Second statement, allosteric inhibitor changes the enzyme active site. Now this is also true. They are actually in their process of disturbing the substrate is that they are changing the shape of the active site. So now the substrate cannot recognize. Substrate means drug. So this statement is also true. Third statement, allosteric inhibitor competes with the enzyme's active site. Now this is not true. This is true only for competitive inhibitor, not for allosteric inhibitor, because they do not compete with the active site, because they always attach to allosteric site. So no question of competition. So this statement is actually false, and this will be our correct option. So option 3 is the correct option. Okay. Here we have a problem. Fronley's adsorption isotherm. We have already discussed it, but related problem, that is problem related to Fronley's adsorption isotherm, now we are discussing. Plot of log x by m, which is mostly remains in y-axis, and log p, that is pressure, it is in the x-axis. It gives a straight line. Now it is that kind of straight line where intercept is also present and slope is there, and intercept value, slope value, both are mentioned. Mass of the gas absorbed per gram of the absorbent, that is basically the value of x by m. We have to find out if the initial pressure is 0.04 atmosphere, and we have to express it. See, the actual value of mass of gas absorbed per gram, that is x by m, this will be expressed as something into 10 to the power minus 4, and we have to find out this something, okay, because it is integer type. So we have to fill in the gap. So this is the equation that we get from Fronley's adsorption isotherm. Now if we take log both sides, the equation will be changed like this. Now we will compare this equation with y equal to c plus mx. So here c is intercept, log k, and the value given 0.4771, okay, and m is slope. So slope is 1 by n. Now 1 by n, the value is directly given, which is 2. So 1 by n value is 2. And from this relation log K value, it is given in the question 0.4771. so from this you can find out antilog. Antilog is basically K equal to 10 to the power 0.4771, or it can also be written as antilog of this. Now here it is given that log 3 equal to 0.4771. so it means what? There is base 10, that means 10 to the power 0.4771, that value is actually 3. And you can also compare here this equation and the equation that is given in the question, and you can easily understand that the value of K will be 3. Fine. So this is one part. Now we know what is the value of K, we also know what is the value of N. 1 by N is 2, so N will be 1 by 2. Now X by M, this value we have to find out. So we are using this equation again, and see, we have written the value of K, which is 3, and initial initial pressure is given 0.04. So it is mentioned as 3 into 0.04 whole square. Okay, and N by N value, that is directly given, which is 2. Okay, slope is 2. So after calculation you will get this value, and you have to arrange this value in this way so that we can understand what will be in this gap. So actually the answer will be 48, because 10 to the power minus 4, that is already given. 48. Density of gold 19 gram per centimeter cube, very high. If this amount of gold is dispersed in 1 liter of water, okay, so this is the dispersed phase, dispersed medium is water, and it is giving us a sol, that means solid in liquid, so it is sol, having spherical gold particles, radius given 10 nanometer, very small obviously. We have to find out number of gold particles per millimeter cube of the solution. There are 4 options. So what we will do, here density is given, mass is given, right? So when density and mass is given, we know that density is mass by volume, but here volume we have to find. So what we will do, mass by density. So it will be 1.9 10 to the power minus 4 gram and 19. Be very careful about the units. Here it is in gram, it is also in gram per centimeter cube. So the value of V you will get in terms of centimeter cube. 10 to the power minus 5 centimeter cube. So this is the volume of this amount of gold particle. This is the corresponding volume, because density is given. Now radius is 10 nanometer. So different unit of length, we will convert it to centimeter. Now 1 nanometer is equal to 10 to the power minus 7 centimeter. So this will be equal to, just multiply 10 to the power 7, so it will be now 10 to the power 6. So this is the radius in terms of centimeter. Okay, next we will find out volume of 1 gold particle. So volume of any sphere, the formula is 4 by 3 pi r cube. 4 by 3, pi value is basically 22 divided by 7, and r we have just calculated 10 to the power minus 6 to the power 3. So now the value we will get in centimeter cube unit, and the value is okay. So the spherical gold particle radius 10 nanometer, volume of 1 nanoparticle is like this. So next what we will do, now we know what is the volume of one particle, and the total volume for this mass, that is 10 to the power minus 5. So we can easily find out the number of gold particles. So for one particle, the volume is 4.19 10 to the power minus 18. You can also understand, see here the power is minus 18, that means it is the volume of one particle. But 10 to the power minus 5, it is the value of all the gold particles. And we have to find out number of gold particles. So we will divide this volume. Suppose this is V and this is V prime. So V by V prime, that will be the number of gold particles. Okay, total volume divided by volume of one particle. Both are in centimeter cube unit. So now the value of, that is the power of 10 you will get. The value will be large. Sorry, this is the number, so there will be no unit. Okay. Next, see, if we look at the question carefully, we have to find out number of gold particles per millimeter cube. So this is not the final answer. Okay, but this is the number of molecules of gold which is present in 1 liter of water, but we have to find out 1 millimeter cube of water, what is the number of particles. So this is the number of particles in 1 liter. Now 1 liter means basically 1 dm cube. So 1 dm cube we will convert to millimeter cube. 1 dm cube, it will be 10 to the power 6 because there is cube. So 1 decimeter, if we want to convert to millimeter, it is actually 10 to the power 2. Yes, but as here we have cube, so that is why it will be 10 to the power 6. So 10 to the power 6 millimeter cube. So this is the number of particles present in 10 to the power 6 millimeter cube, but we need the number of particles which is present in 1 millimeter, right? So the last and final part, ten to the power 6 millimeter cube contains 2.4 10 to the power 12 particles. So 1 millimeter cube, simply divide it by 10 to the power 6. And this will be 2.4 10 to the power 6. Okay. So which option correct? Last option. So option 4. So always when you are getting a very, that is, it is lengthy question and also complex, always do it part by part. First of all, you have to make sure what are the informations that are given and what exactly we have to find out. Because if you stop at this position, this is actually not the correct answer, though up to this our approach is correct. But if we do not do this last part, ultimately the result will be wrong. Okay, so be very careful about the units also, because if the units are not same, then even if you are following the correct method, then you will be getting wrong answer. Okay, so what are the informations that are given? Accordingly you have to solve it step by step, and units must be keep in mind whether it is same or not. Okay, and finally the actual question that are asking, we have to read it very carefully. Classification based on nature of interaction between dispersed phase and dispersion medium. So now we are going to classify the colloids. Now remember, this classification, it is based on interaction between dispersed phase and dispersion medium, because there is another type of classification that we will also see. So that is why it is important to mention it is based on what. So it is based on the nature of interaction between these two part. One is dispersion medium, another one is dispersed phase. So this is the basis of classification, affinity between these two. So if there is affinity, then there will be one type. If there is no affinity, then there will be another type. Okay, so it is basically two types. Affinity present, one type; affinity not present, another type. So the first type is lyophilic. Now the meaning of the word phil, that is actually affection. That means when we are saying philic, there must be affinity present between these two phases, that is dispersed phase and dispersion medium. So from the name you can directly understand lyophilic. And there is another type which will be phobic, because phobia is fear. So that means it has no affinity between them. So lyophilic colloids in this type of salts, see, it is also sometimes that is colloids are called salts, because salts is one type of colloid. There are different types of colloid, but salt is one of them. In this type of salt, there is strong affinity between this dispersed phase and dispersion medium. And important characteristic of these salts is that, suppose the dispersion medium is separated from the dispersed phase. So suppose there is water and you have dissolved some solid and you are evaporating the dispersed phase, that is water. So there will be dispersion medium left only. Now if you again want to make that salt, you can reconstitute it by simply remixing the dispersion medium. So you have removed it by evaporation. Suppose it is water, so that is why we are calling it evaporation. But if you are adding again the same amount of water that you have evaporated, then again you will get back the original salt. So because of this type of property, it is also known as reversible salts. Fine. Next very important property of this, which is not for lyophobic, is that stable. They are stable. So as it is stable, obviously they will not be easily coagulated. Okay, so when we are saying that it is not stable colloid, that means there will be coagulation. Now coagulation, the rate, it may be high or it may be slow. It may be dependent on whether you are adding something from external side or not. Okay, but the main important thing is here it is stable. That is the reason coagulation is not easy. It can be obtained by mixing substances like gum, gelatin, starch, rubber, etc. with a suitable liquid. So these are some of the examples. And remember, sometimes lyophobic, it is also called hydrophilic. But when obviously the dispersion medium is water, because hydro, this term is derived from water. Okay, so it can also be called hydrophilic colloids. Similarly, suppose if there is any other solvent, so there may be, the name can be changed, but the important thing is this philic part, that is constant, because there is affinity present between dispersed phase and dispersion medium. Other type is, that is the second type, is lyophobic colloids. So now there is no affinity. Examples: silver, gold, metal sulfides. So in the previous case you have seen the examples. Remember, it is rubber, gelatin, gum, like this, polymeric in nature. But here we have some inorganic compounds, silver, gold, metals, that is, and metal sulfides also. Then aluminium hydroxide, etc. When it is mixed with dispersion medium, they do not form colloidal salt. So see, naturally there is no tendency to form colloidal salt. That means it is so unstable. So that is the reason forcefully we have to make it. And forcefully make it means you have to apply some special techniques. Then only you can make lyophobic colloids, because they have as there is no affinity between them. So obviously, if we are not using special technique, we cannot make it. Even we are making it, it will be easily, that as it is unstable, its lifetime will be very low. Okay, so these are unstable as they readily precipitated or coagulated on the addition of small amount of electrolyte. This is one process. You can make the coagulation very easy. Actually, their stability is so low that even you are adding very small amount of electrolyte, then also there will be precipitation or coagulation. That means it is no longer stable. Even by heating and shaking. Okay, and once it is precipitated, they do not give back the colloidal salt by simple addition of the dispersion medium. So in the previous case you have seen it is possible, so that is why it is reversible, but now it is irreversible because we cannot get back the original salt. They need stabilizing agents so that we can keep them for longer time to increase their lifetime. And just as we have mentioned before, when water is taken it will be called hydrophobic, but main part is this portion, that is phobic. Okay, when water is present it is hydro. So these are the two types of, that is we have classified colloids on the basis of whether affinity is present between dispersed phase and dispersion medium or not. Now we will compare these two, though we have already seen some properties, but if we summarize it, it will be, so stability, obviously because of hydration they are quite stable. Now here it is mentioned hydration. Now hydration word, better we use the word solvation. You can also write it as solvation because solvation is general term. When the solvent is water, then you can call solvation as hydration. But as there is actual, I am trying to say, as there is affinity present between dispersed phase and dispersion medium, so obviously the particles will remain solvated. So because of this solvation they are quite stable, not coagulated easily. But here that is not the case. They get coagulated by heating very easily, or if you are agitating them or shaking them or heating them, okay, or small amount of electrolyte. Then reversibility, reversible, irreversible. Visibility. Now visibility of colloids we have already discussed when we have compared true solution, colloids and suspension. But see, when it is the question of visibility, in case of lyophilic and lyophobic, though both are colloids, there is some difference. The dispersed particles are neither visible nor detected easily even under ultra microscope, that is very powerful microscope. But in case of lyophobic, normal condition, that is with naked eye we cannot see, but with powerful microscope like ultra microscope we can do so. Okay, so this is the difference in visibility. Viscosity. The viscosity is much higher than that of dispersion medium. Now what is viscosity? In a very simple statement we can say that it is the resistance for liquids, that is fluids mainly, it is the resistance of the fluid to move. So if we are saying that something is highly viscous, that means its tendency to flow will be very low. So just take the simple example of water and honey. Honey is more viscous compared to water, so that is why its movement compared to water it will be very slow. Okay, so here viscosity property, if we compare between this lyophobic and lyophilic, here it is much higher, but in this case it is almost same as that of dispersion medium. Next, some more properties. Surface tension. Now surface tension is basically the tendency of the liquid to remain in the area which is as minimum as possible. Because if we consider, suppose in container there is any liquid, and if the molecules that is present in the bulk and the molecules that is present in the surface, the forces that are acting on these two types of particles different. Why? Because here the interaction with water particles or any other solvent particles, it is from 360 degree overall. Okay, but here if we consider surface particle, the forces are not balanced because this side is total, there is no water molecules. So that is the result. For surface molecules there will be some extra pressure, extra tension will be present. So that is the reason that we see that drops of liquid, they are mostly spherical in nature, because the shape sphere that involves minimum surface area. So this is all about surface tension. So this surface tension, it is usually lower than that of the dispersion medium. Here it is nearly same. So both for viscosity and surface tension, these two are nearly same in case of lyophobic, but in case of lyophilic, viscosity is high but surface tension is low. Charge on particles. Dispersed particles have little or no charge on them. Now these charge on particles, this is basically one of the important property of colloids. We will discuss it later in detail. Right now just remember that dispersed particles have little or no charge on them, but dispersed particles in case of lyophobic, they carry a definite charge. Now this charge may be positive or it may be negative. Migration of particles in an electric field. Now as there is charge particles present, so if we place electric field, dispersed particle may migrate in either direction or may not migrate at all, because here we do not have any specific charge. So when we are applying electric field, obviously there will be no such specific migration. And in case of lyophobic, as there is particular charge is present, it may be positive, it may be negative. So depending on the nature of the charge present, whether it is positive or negative, dispersed particles can migrate in a particular direction. That is, depending on depending on positive or negative, it may move towards cathode or anode. Fine. Stability, it is thermodynamically stable, thermodynamically unstable. Tyndall effect, though we have not discussed yet, but remember in Tyndall effect, this is very specific for colloidal particles. When we have compared true solution, colloid and suspension, then we have seen that Tyndall effect, it is only for exclusive for colloids. But under colloid, if we compare these two types of colloid, then here Tyndall effect present, but it is weak. Here it is strong. Okay, so these are some of the differences between these two types of salts. Next, another type of classification now we will do. The previous one is based on affinity between dispersed phase and dispersed medium, but now classification is based on the type of particles of the dispersed phase. So now we have nothing to do with the dispersed medium. We are interested only in the dispersed phase particles. Okay. We have already seen that colloidal particles present in colloidal system, their size vary in this range. Now, depending upon how different substances forming colloidal solution acquire the size of particles in this range. Now this range is there is a particular range, but among this range also there may be different size. Fine, some may be close to 10 to the power minus 7, some may be close to 10 to the power minus 5. So depending upon how different substances forming colloidal solution acquire the size of particles in this range, and they may be classified into 3 categories. The first type is multimolecular colloids. When large number of atoms or small molecules having diameter less than 1 nanometer, that means if you consider this individual small molecule, the range is not in the range of colloidal particles, but when they are combining together, they now will have the size range between 1 nanometer to 100 nanometer. Fine. So small molecules of a substance combine together in a dispersion medium to form aggregates having size now in the colloidal range. Before it was not, but now after combination it is in the colloidal range. The colloidal solution in this way, if it is formed, it is called multimolecular. See, if you observe the name carefully, multi-molecules. So multi-molecules means what? Very small molecules together will combine and it will make aggregated particle. Okay, so just remember the name carefully, then you will be easily understand, that is, you will not be confused between different types of colloids. Okay, the species, atoms or molecules constituting these dispersed particles in multimolecular colloids, they are held together by van der Waals force. Okay, so there may be a question that what type of force is actually responsible behind the formation of multimolecular colloids. So answer is van der Waals force. Gold salt may contain particles of different sizes composed of several atoms of gold. So this is one of the example. Similarly, for sulfur salt, it consists of particles containing about 1000 of S8 molecules. So if you consider individual S8 molecule, it will not be in the range of colloidal particles. That is not in range of 1 nanometer to 100. It will be less than 1 nanometer because it is very small. But if 1000 of S molecules now together, the size will be in this range, that is 1 nanometer to 100 nanometer. Okay, so this is multimolecular colloids. The second type, macromolecular. Now see, macro means what? Very large. That is opposite word of micro. So macromolecular means now the molecule itself is very large. It is not that small molecules combining then you are getting the colloidal range. No, directly it is very large. Certain substances form large molecules whose dimensions are comparable to those of colloidal particles. Now since these molecules are very large, so obviously their masses, molecular masses will be very high. That is the reason they are called macromolecules. When such substances are dispersed in suitable dispersion medium, the resulting colloidal solutions, that will be known as macromolecular colloids. And remember, most of the lyophilic salts falls under this example. So lyophilic salt we have already seen, another type of classification. These colloids are quite stable because it is lyophilic type, so obviously they will be stable, and there is some resemblance with the true solution in many respects, not in all respects, otherwise it will not be called colloid. Only in some respect there is some similarity or resemblance. For example, colloidal dispersion of naturally occurring macromolecules. Naturally occurring large molecules means starch, protein, gelatin, cellulose, nucleic acid, etc. So all are examples of macromolecular colloids. Now it is not just limited to natural particles, it may be also synthetic macromolecules. So that means man-made. So this type of polythenes, nylon, polystyrene, synthetic rubber, they can also form macromolecular colloids when dispersed in suitable solvent. This is the second type. Now the third type, third and last type, and also this is the most important because under this third type there is so many other things that we have to know. Associated colloid, micelle. So in bracket it is written micelle. So what is micelle? Colloids which behave as normal electrolyte at low concentration. So suppose the concentration is very low, number of particles per unit volume, that is very low. But if the number of particles per unit volume is now high, that is concentration is increased, now they will be acting as colloidal particles. They will be showing colloidal properties. Try to understand the difference with the multimolecular colloids. In case of multimolecular colloids, it is we have mentioned nothing about low concentration or high concentration. We have just said that if the number of particles that is combined together, they form large particles. But in this case, it is different. Here also aggregation is present, but it is different type. At low concentration, there will not be any aggregation. Only at a particular concentration, due to formation of aggregated particles, now they will form aggregated particles, and that will be now in the range of 1 nanometer to 100 nanometer. So that is why it is called, it is different name, it is not multimolecular, it is associated colloid, and the aggregated particle, it is given a special name which is known as micelles. Okay. Here we have a picture. See here this zigzag line, it is hydrophobic tail. Now tail, it is we are calling it tail because it is tail like nature, and hydrophobic means it is mainly made of carbon and hydrogen. So that is why it is hydrophobic, because it is non-polar. So there will be no interaction with water properly. And this red part is hydrophilic head. We are calling it head because it is having cylindrical type of shape. Okay. And this blue particle, it is the water molecules. Now hydrophilic, that means it has affection for water. So obviously this red part, that will be towards water molecules because all these are water molecules. And the tail part, that is the hydrocarbon part or hydrophobic part, that will be facing the opposite of water. So that is why in the surface there will be only the hydrophilic part, but inside there is hydrophobic part. So this is the picture of micelle at high concentration. Though mostly micelles, when it is fast formed, it is spherical in nature, and there are different types of other shape for micelle present, but that is not important for our syllabus. The spherical micelle example is enough. Okay. The micelles are formed by the association of dispersed particles. But remember, here we have simply mentioned low concentration, there is no association, high concentration, association. But this is a qualitative term. But it must be quantitative. That is, what is the exact concentration when micelle will be formed. So this exact concentration, that is actually the minimum concentration that we must reach if we want to get micelles. So this minimum concentration below which you cannot get micelle, above which you can get it. So the micelle are formed by association of dispersed particles above a certain minimum concentration, and this concentration is known as critical micellization concentration, in short CMC. Now this value of CMC, obviously it will depend on the nature of dispersed phase, that is what type of molecule you have taken, it will depend on that. And this type of colloids, that is associated colloids, mainly formed by surfactants. Now what is surfactants? Surfactants is basically surface active agent. We will go in detail for surfactants, but here simply it is mentioned that it is surface active agents, and surfactants are mainly soaps and synthetic detergents. Okay, now what is surfactants, what are the different characteristics, we will get to know in other slide. Classification of surfactant. So surfactant, in the previous slide you have already understood from this particular picture, there will be a hydrophobic part which is tail like shape, and there will be a hydrophilic part. Okay, this type of picture. Now depending on the what type of groups are present, these surfactants, it may be 4 types. So the first classification is whether it is ionic or non-ionic. Now under ionic, 3 possibilities are there. If it is carrying positive charge, it will be cationic, negative charge anionic, and if both positive negative charge are present, it will balance each other. So it will have Zwitter ionic type of character, that is amphoteric. So basically it is total 4 types. Okay, so non-ionic, you see we have not mentioned any charge. If it is cationic, the polar head that is carrying positive charge, anionic, polar head carrying negative charge, amphoteric, polar head is carrying both the charges. It can also be called as Zwitter ion type. Zwitter ion means when both positive negative charge exist together. Okay, so these are the classification of surfactants, and we will also see some more characteristic for this all. So when it is anionic, okay, first start with non-ionic. Hydrophilic group has no charge but derives its water solubility from highly polar groups. Now you may one question may arise in your mind that there is no charge, then how it is hydrophilic, how it will interact with water? It is possible even without charge, because here we have highly polar groups such as polyoxyethylene, OCH2CH2O, or polyol groups. So because of presence of this type of groups, though there is no charge, but still they can be hydrophilic. Look at these examples. Then we have anionic. So now in the hydrophilic head there will be negative charge, such as negative charge may be carboxylate ion, sulfonate, sulfate, like this. So this is it is Y. Sodium total surface, HTS, very common example of anionic surfactants. And I will suggest you that if it is better if you can remember some of the examples, that is some examples of anionic surfactants, some examples of cationic surfactants, because some numericals may not numericals, some questions may be there which will just mention one molecule, and it may be asked that what type of surfactant it is. So if you do not know the structure, you will not be able to understand. Though this is simply memory based question, but still if you do not remember the structure, you will not be able to understand whether it is what type of nature the surfactant has. Okay, so that is it is important, remember some of these. I am not saying that remember full formula, that is not that will be difficult, but at least try to remember what is the nature of the polar head. Okay, and don't think that as Na plus is present, why it is not Zwitter ion. Okay, but that is not the case here, because Na plus it is just the counter ion, but the actual group which is attached to this long tail, that is negative. Na plus will obviously there because that is the counter ion, but don't think it is amphoteric, that is zwitterionic. No, that is not. Only the part that is attached to tail, you have to be you have to focus on that part only, not the counter ion. Cationic, hydrophilic group carrying positive charge, that is quaternary ammonium halides. See, this is the R group here, and counter ion is Br minus, but we are interested only in this part as it is carrying positive charge, it is cationic surfactant. And the last type, amphoteric or zwitterionic, it's these molecules present both the ionic and cationic groups, and depending on pH, its prevalence, that is whether it will mainly exist as anionic or cationic or neutral species, that is completely dependent on pH. So suppose if the pH is that is towards basic side, obviously the acidic part will be neutralized, and basic part, that is anionic part, that will prevail. Okay, and vice versa. Here we have example CH3CH2 N plus Me2, and there is another part which is CH3COO. After that the name is started, DAB in short. Okay, and if directly the pictures are given in the question, then it is fine, then you will be easily understand which one is anionic and cationic. But again I am saying, don't focus on the counter ion, because counter ion will always be there, but that doesn't mean that it is not cationic. Okay, so these are the 4 types for, that is different types of surfactants, depending on what type of groups are actually present in the head, because tail part is common for all, right? Characteristic and application of surfactants. Its applications are actually very wide. Okay, surfactants are interfacially active compounds, consist of polar head group, non-polar hydrocarbon chain. Now why it is called surface active? Because it decreases the surface tension. So when you are adding surfactant to liquid, or suppose simply take water as example, then surface tension basically decreases. Okay, so that is why it is called surface active agent, that is the surface tension is decreased. Now they are preferentially adsorbed in the interfaces between two liquids, or it may be a gas and a liquid, or it may be a liquid and a solid. So the most common example you can take, gas and liquid. So if this is the liquid surface, this is the gaseous surface, right? Now the molecules, that is the surfactant molecules, if they are present here, that is in the interface of gas and liquid. Okay, so as in concentration will increase, gradually what will happen, all the surface it will be occupied. Okay, and once we reach CMC, critical micellization concentration, then they will start forming micelle. As the concentration of surfactant increases, adsorption takes place at the surface until it is fully overlaid. That means the process will continue as long as the surface is not saturated. But once the surface area is saturated completely and you are adding surfactant further, now micellization will take place. Okay, so these are the steps by which micelle can be formed. Surfactants also have a number of other useful properties, including emulsifying or dispersing power. So emulsion, that is a type of colloid, it will be discussed separately, but here just remember it is used for emulsifying any other substance. It helps in emulsification, that is why it is emulsifier. It helps in wetting. As I have said that surface tension is decreased. So suppose you have taken water droplet, it is on any surface, but when you have added surfactant to the water and then you are spreading it on the surface, what will happen? Now surface tension decrease, so it will spread out and it will wet the surface. But here wetting process is not possible because of surface tension. It will remain in sphere shape, that is a water droplet, it will remain in sphere shape because it will try to remain in minimum surface area as much as possible. But when you are adding surfactant, now surface tension is decreased, so it will spread out like this. So that is why it helps in wetting or spreading, and also foaming. So foam is also one type of colloid. So basically it helps to form different types of colloids. They may act as detergents, so these are that is practical application: foaming agents, emulsifier, dispersant. Okay, so these are the different field in which it is used. See how versatile it is. And without surfactant, washing laundry, it is our daily requirement. It will be difficult, and many of the common food products like mayonnaise, ice cream, it will not exist. So these are the important applications of surfactant. Okay. Micelle and its formation. So micelle form by orienting the hydrophobic portion of the surfactant, that is the tail portion, towards the core of micelle. So this type of picture we have already seen, and the head that will be in the outer surface, because outer area there is water. So see here we have example of the soap molecule C17H35. So this is the hydrophobic tail, this is the hydrophilic head. This is another picture, and you can also draw the picture in this way. So this is the hydrophobic part, this is the hydrophilic part. Okay. So see, this is the picture. Here all the tails are towards that is opposite side of water, because outside we have water. So this is the picture when you are looking at it directly, but if this is the side picture. Now see here, oil, obviously if there is water as well as oil and you are adding surfactant, then the oils will be attracted towards the tail, because oil is also, it is non-polar in nature, it is not like water. That is why oil and water, they do not mix to each other. Okay, so oil, that is the grease that is present in when we wash our clothes, that is when we use surfactant as detergent or soap, then this is the mechanism by which it can remove dirt or grease from the that is dirty surface or dirty clothes. Okay, so oil part, it is here, this is the oil part. So this is the structure of micelle, but inverse micelle is also possible, though that is not so common. So but you should know what is inverse micelle. It can also be formed in non-aqueous medium. Suppose now outer region, that is a dispersed medium, it is not water, it is something non-polar. Then obviously now what will happen? The tail part will be outside and the head part will be in the core. Okay. So look at this. Now if there is oil and water mixture and oil is present in large amount, then water is present, it is interacting with the head part, and oil is outside. This is oil and the tails are towards oil side. Okay, so this type of micelle, it is known as inverse micelle. Fine.